Okay, so our next topic has to do with inverse functions. Inverse functions. Now, before we talk about an inverse function, we're going to talk about the concept of a one-to-one function. A function S is said to be a one-to-one function if each number in the range of y of f is associated with exactly one number in its domain x. That's a one-to-one function. For a one-to-one function, any horizontal line intersects with only one point in the graph. So remember we had the vertical line test, and the vertical line test told us if something was a function or not. If we trace the vertical line to the graph of a function, the vertical line should only intersect in one point, and that means it's a function. Now, before we go into talking about inverse functions, let's talk about this one-to-one relationship. Bring out the type. Oh, it's hidden. Thank you. So let's look at a couple of examples here, and let's see this. I'm gonna draw two graphs. I'm going to draw the graphs of two functions. So the first graph is going to be this function here. This graph is y equals f of x equals x to the 3. Then I'm going to draw another one here that's going to be something like this. This is y equals f of x equals x squared. Okay. Now we know both of these are functions because if we do the vertical line test, I'm going to do that in pink. If we do the vertical line test at any point of the graph, it's only going to intersect in one point. So these are functions. Now, the horizontal line test is to determine if a function is a one-to-one function. And it's important to identify a one-to-one function because only one-to-one functions have inverses. Okay? Or we can only calculate the inverse of a one-to-one function. So for example, for this graph here, if I trace a horizontal line, what happens? It only intersects in one point. And I can draw that in any point of the graph. And it only intersects in one point. Okay? So since the horizontal line only intersects in one point, well, first this is a function. That's a pink one. So it is a function. And is it a one-to-one? It is. Because it only intersects in one point. Now, if we look at over here at the other one, at the y equals f x squared, is it a function? Yes, we've already established it is. Now let's look at the horizontal line test. If we do this, we're going to see that the graph is going to intersect in more than one point. So is it a 1-to-1?
No.
It is not. Now, again, why is this important? Because if we want to calculate, and we're going to see how to do that in a bit, if we want to find the inverse of the function, we are going to be able to do it for this one, but we are not going to be able to do it for this one. Okay. And so what characteristics is there for a 1-to-1 function? In the case of the 1-to-1 function, notice that for any value of x, there is only one value of y. In this function of x to the 3, if I grab any value of x, let's say this value here, there is only going to be one value of y for this function. However, if I grab any value of x, I'm sorry, if I grab any value of y, it only has one value of x. However, if I grab any value of y over here in this graph, I'm going to see that this value of y has a value of x on this side, and it has a value of x on this side. So that means that's why it's not a 1-to-1 function. Let's take a screenshot of this. Okay, questions with this one? Okay, so assuming that we've got a 1-to-1 function with a domain x and range y, the inverse of f is going to be called f to the -1. This is important because it can be confusing. It's f to the -1. That doesn't mean it's 1 divided by f. Okay, so just as a note here for the notation we're going to be using. So we're talking about f to the -1 of x. This means inverse. F of x to the -1 is 1 divided by f of x. These two are different. Okay, so when the -1 is right next to the letter of the function, that means that it's a notation to describe an inverse function. It doesn't mean that that's the reciprocal in mathematical notation. And so if we have f to the -1, if I substitute the inverse of the function within the function, I get x. And if I substitute the function within the inverse, I also get x for every value in the domain in the range. So let's look at some examples. Well, let's first talk about some properties. So since there's a relationship between the function and its inverse, there are some properties of inverse functions here that are important. The domain of the function is going to be the range of the inverse, and the range of the inverse is going to be the domain of the function. So the domain and the ranges are inverted. Y equals x, f of x is equivalent to x equals the inverse function of y. The inverse function is also going to be 1-to-1. Okay. And if I substitute the function within the inverse or vice versa, I'm going to get the original function. And the inverse of f is unique, meaning there's not going to be any, there is only going to be one inverse of the function or one version of the inverse of the function. And these are going to be the properties. Okay. So let's find the inverse of these three functions. Let's see how we do that. Before we find the inverse, we need to identify if the function is a one-to-one function. Once we find out if it's a one-to-one function, then we can find the inverse. So let's do these three examples. I'm going to jump over here to so let's look at the first one. First one says f of x equals 5x minus 7. So first one says f of x equals 5x minus 7. Okay, and first thing we need to do is see if it's a one-to-one function. And let's practice what we just learned regarding one-to-one functions. Let's practice as well the graphing of functions. Okay, so what type of function is this one? This one is a line. Okay, so the base function is y equals x, which would be this one. I'm just going to go step by step like we've done with the others, and I'm going to use some color coding here. Y equals 5x. It means we're making it a little bit more closer to the y-axis. And lastly, y equals 5x minus 7, it means it's being shifted down 7 units. So now we've got the minus 7 here, and the line would be going something like this. So that is our function there. And here, this number here would be 5, just to find that intersection there. So 5x minus 7 equals 0. This means that x equals 7 divided by 5. So this number here is 7 divided by 5. And that would be, the green one would be the graph for that function. Now, if we apply the horizontal line test to the green one, remember, in any point, we're going to see that it intersects only in one point. So is it one-to-one? Yes or no?
Yes.
It is. So if it's a one-to-one function, that means that the function, we can find the inverse of the function. How do we find the inverse? Finding the inverse. Basically, to find the inverse of the function, we're going to substitute x for y and y for x. It's the first step, and the second step is solve for y. And so what we're going to be doing is the following. We're going to take the original function. The original function is y equals 5x minus 7. And what we're going to be doing is substituting the y for an x and the x for a y. And we are going to solve for y. So we're going to send the minus 7 to the other side. It's going to be adding. And then we're going to have y equals x plus 7 divided by 5. Lastly, y equals x divided by 5 plus 7 divided by 5. This function that we just found here, this is the inverse of the original function that we This is the inverse of the original function we had at the beginning. Okay. Okay. So again, first we validate that it is a one-to-one function. Once we validate that it's a one-to-one function, we simply substitute the x for y and y for x, or substitute the two variables, solve, and we're going to find. Yes?
So if it's not one-to-one, it's not, it doesn't have an inverse, right?
It doesn't have an inverse. And the thing that's happening here, if we were to graph this function, it would be, so this is going like this to the top. It would be going in the opposite direction. So that's why it's called the inverse. Right now here, the inverse of the function, isn't really, it doesn't kind of pop out how we could apply it. But yes.
If I were to have a graph, and that graph was not one-to-one, but I do have like the equation for a portion of the graph, can I find the inverse of that portion, or just because all the graph is not?
That's a good question, because it comes back to the piecewise functions, the functions that are defined in sections. Okay, so yes, we can do that for a range. Oh, okay, so that's a good observation, Daniel, and it actually goes to what I was going to talk about in a moment. So what you're saying is I've got a graph. And let's talk about the example that I gave. So remember that we talked about the parabola. The parabola was like this. So this is not a one-to-one function, and I can't calculate the inverse. However, if I say that I'm not going to talk about the whole parabola. I'm just going to talk about a part of the parabola or a section of the parabola, which is this one. Because if you would, I hope you agree that if I just look at this part of the parabola, this part of the parabola does comply with the horizontal line. So I could calculate the inverse of y equals x squared for a range from 0 to infinite. If I mark it just for that range, then I can find the inverse for that section. And that actually takes me to the example I was going to give. Right now, these inverse functions for these examples might not make much sense, but you guys have used inverse functions already. Remember when you calculate, you know the trigonometric functions, right? Sine, cosine, and tangent, right? And I can calculate the sine, the cosine, and the tangent of an angle, right? But remember that your calculators have the inverse sine, the inverse cosine, and the inverse tangent, where if I have a value of the relationships, I can find the angle. It's this, it's the inverse. However, remember that, how is the graph of a sine function?
You take a bunch of pieces.
It's periodic, exactly. So a sine function is like this. The trigonometric functions are periodic. So by default, these do not comply with the horizontal line rule. So how can I calculate the inverse of a sine? Or how can I use the inverse of a sine? Actually, the inverse of a sine is restricted to this range, which is from 0 to pi. So we are going to be able to calculate the inverses of sine, cosine, and tangent. That's actually one of the next topics. But it's not for the whole range of the function. It's just for a part of the range of the function. Is that clear? That answers the question. And this is very common. Now, you guys are going to present, I think, house algebras. You've got logarithmic and exponential functions. Actually, it's the same thing. The exponent and the logarithm, they're inverse functions of each other. Just in those case, an exponential or a logarithm, those are one-to-one by, those are going to be one-to-one by default. Okay, questions with this one?
Teacher, so
Yes.
one-to-one functions are going to be the one there where the x is eleved by an odd number.
That's a good observation. The even functions the even power functions are not going to be one-to-one. Okay, the even power functions that are whole numbers are not going to be one-to-one. So x squared, x to the 4, x to the 6, etc. But x to the 1, x to the 3, x to the 5, the odd ones are going to be one-to-one. So that is a good observation. And that has to do with symmetry. Remember that we talked about symmetry? So an even function has symmetry with regards to the y-axis. If you have symmetry with regards to the y-axis, the horizontal rule is not going to be able to be applied because the same thing you have on the right, you're going to have on the left. Okay, so that's a good observation, Cohen, and you're correct. Okay. I'm going to clear this and let's look at the next one. The next one we already saw that it's I'm sorry, we already saw that it's one-to-one. So the next one is y equals x to the 3. And we already saw that this function is one-to-one. Just to reinforce here the idea of this, and we do the horizontal line rule. It is one-to-one. And so we follow the two steps. So first, we substitute x for y. Y for x. And lastly, we solve for y. This one is relatively simple. So the original function is y equals x to the 3. So basically, we're going to have x equals y to the 3. And then we just solve for y. So y is going to be equal to the root 3 of x. And this is the inverse.
Does the range of the domain change?
The range and the domain of the original function get flipped or inverted for the new one. So the range of the original is going to be the domain of the inverse, and the domain of the original one is going to be the range of the inverse. Okay, so in this particular case, both the range and the domain of the original function are minus infinite to infinite. So the range and the domain of the inverse function are also going to be minus infinite to infinite. Okay. Let's do one last one, the last one. And the last one is f of x equals 1 divided by x minus 3. Okay, so let's look at this one. Again, let's practice the graphing. The sketching of the graphs. So the original base function for this is y equals 1 divided by x. That looks something like this. That's a power function. It's a power function. Then I've got y equals 1 divided by x minus 3. What is the x minus 3 going to do to that graph? What is the minus 3 going to do? Remember the shift. What type of shift is that?
It's to the right.
It's going to be a shift to the, it's going to be a horizontal shift, first of all, because it's inside the function. The minus 3 isn't outside the base function, it's inside. So it's going to be a horizontal shift. Since it is negative, the shift is going to be to the right. So it's going to be moved 3 units to the right. So basically what I'm going to do here is I'm going to draw an imaginary axis here at 3. Basically what's going to be happening is that function is going to be moved 3 units. To the right. So it's going to be the green. And so if I apply the horizontal line rule, we're going to see that it only intersects in one point. So this means that, is it 1-to-1? It is. And we're gonna find the inverse. So one is substitute X for Y and Y for X. And two, solve for Y. So the original function is Y equals 1 divided by X minus 3. So we're going to substitute X for Y and Y for X. And we're going to solve for Y. So I'm going to send the Y minus 3 to one side and the X over here to the bottom. And I'm going to send the 3 to the other side, adding. This is going to give me Y equals 1 divided by X plus 3. And this is going to be the inverse. Okay, questions with this one? Is the procedure relatively clear? Okay. Okay. So, this is appropriate because I was going to mention the symposium. We're going to be talking about transcendental functions. And so the symposium is called Trascendencias. It's historically called Trascendencias. I was the professor responsible for the first Trascendencias back in 2001. Before the engineering symposium has a cool history. It is the only event at CETIS that's a student-driven event. And actually, I think it's the only event at CETIS that has gone on uninterrupted since its creation. So it's more than 30 years old, and there's never not been an engineering symposium. But it was, this is just a bit of CETIS engineering history. It wasn't always called Trascendencias. But from the beginning, it was always called the Engineering Symposium, and every year it had a different name. But in 2001, we decided with the students that were in the organizing committee that we wanted to give the symposium a branding. And so one of the students came up with this thing, this concept called Trascendencias, which, by the way, I don't think the word exists, actually. So if you look at it in the dictionary, I don't think Trascendencias exists. And they came up with this cool idea that the logo, I don't know if they still have the same version of the logo. I haven't seen the publicity. but the original logo, it was actually a blue motif, was a circle that had these sine waves.
Oh, it's the same.
Kind of the same still.
I think it's still the same.
So maybe a little bit modified, a little bit, but it's kind of the same concept. And the idea of the, do you know what the sine waves mean? Each of the, well, in the original concept of the logo, each of the sine waves represented one of the academic programs at CETIS. So it's mechanical engineering, cybernetics, mechanical, et cetera. And so
Oh, yeah.
that's where Trascendencias came along. And it was
There's 7.
there should be 6 or there should be 7, I think. There should be 7 if we include the whole CETIS system. And so that's where Trascendencias came on. So we're going to be talking about transcendental functions. So a transcendental function, there's a group of functions in math that are called transcendental functions. I'm not sure why such a dramatic name, why they're called transcendental functions. These are functions that do not satisfy a polynomial equation. So they're functions that cannot be represented by by a polynomial. So in contrast to any algebraic function, like the ones we've been seeing up to this point, if they can be represented as a polynomial. So what are examples of transcendental functions? Exponential, logarithmic, trigonometric functions are examples of transcendental functions. And what we're going to be talking about next have to do with trigonometric functions. And so the trigonometric functions, and you guys know these are the typical, you guys have seen them before. These are the sine, cosine, tangents, and their reciprocals or their inverse functions. So these are called trigonometric functions because they help us express relationships for certain trigonometric figures, which are particularly triangles or right triangles. So assuming that we've got, let's assume that we've got the Cartesian plane and we've got a circle in the Cartesian plane that's called a unit circle. Why is it called a unit circle? Because the radius is 1. So, so if we look at the function here, it crosses here at 1, 1, minus 1, and minus 1. If we were to draw a triangle, we were to create a natural right triangle here, where the hypotenuse of that right triangle is the radius, and the radius is going to be equal to 1. And we were to establish 2, let's say, coordinates. Let's call this one x, and let's call this one y, of the point of intersection here. So this coordinate is x comma y. Then the sine and cosine relationships are expressed in the following way. First of all, we're going to know that in this triangle, if we use Pythagoras, x squared plus y squared is going to be equal to 1. And so the sine, if we look at the angle here, and we call that angle t for now, the sine of the angle is going to be the opposing side dividing by the hypotenuse, which is going to be y divided by 1. And we're going to call the cosine the adjacent side divided by the hypotenuse, which is x divided by 1. Since the hypotenuse is 1, then the sine of t is equal to y and the cosine of t is equal to x. That's why usually with regards to the sine and the cosine functions, when we're looking at a right triangle that's represented with regards to coordinates, the sine is always going to be related to the opposing side, which is the y, and the cosine is going to be related to the adjacent side, which is going to be the horizontal or the x. That's kind of like the formal, let's say, mathematical definition of the sine and cosine. And there are some variations here. So the basic functions are sine and cosine. But again, if we've got our unit circle here, and oops, monkey circle there. And we've got our triangle here. And so this is x, and this is y, and this is 1. There are some other trigonometric functions that are derived from this. So there's the tangent function that's going to be the opposing side divided by the adjacent side, which is y divided by x. And then these are going to be the reciprocal. Again, these aren't the inverse. These are the reciprocal functions. And so we've got the second, cosecant, and cotangent. Cotangent is the same as 1 divided by tangent. The second is the same as 1 divided by cosine, and the cosecant is 1 divided by the sine. And these are the 6 functions that we usually work with. The sine and the cosine are the base functions. So I've got sine, cosine, tangent, cosecant, secant, and cotangent, which are the reciprocals, not inverse, the reciprocals of tangent, sine, and sine, cosine, and tangent, respectively.